Well, hi everybody. Welcome to week 3 in the Python for Biologists course that we're running here. This is, when we finish today, we'll be at the halfway point through our six topics. I've decided to reopen with the flowchart because it helps remind us where we are. We're now, because of last week, at a place where users can provide the name of a FASTA sequence database to the FASTA Sniffer. If they fail to provide that information, we report a usage message to the screen. But we haven't yet done anything to check whether that file name that they've handed us is actually usable. So we will be doing the file operations as part of this week's topic. So I'm going to try to talk a little bit about how file access works. And then we can start doing things like opening a FASTA file for reading, which is just a big text file, you recall. Being able to go on through the process of reading it and so on. But I wanted to start with this little painting from Rene Magritte. This is part of his series, The Treachery of Images. Have you seen this piece of art before? I think he's a Belgian fellow. In any case, what he's written in French here is "Ceci n'est pas un pipe." Does anyone study French? Ah, okay. Well, I took high school French, so I would point out that what this inscription means is this is not a pipe. So why would somebody paint a pipe and then write underneath it, this is not a pipe? He's trying to remind you that a pipe is a physical object that you smoke. But this is so much oil arranged on a canvas. So insofar as this is a representation of a pipe rather than a pipe itself, he's written this helpful reminder that this is not a pipe. Now that might seem like a very weird place to go with this lecture, but I want to point out that we're going to be dealing with lots of things that are not files, but we must make use of them en route to a file. So I'd like you to get accustomed to the idea that there are 4 different things going on in just this little bit of code that we're doing today. We start with the FASTA file on disk. So we frequently call FASTAs databases, right? We call them sequence databases. But very helpfully, FASTA databases are not written in any sort of database format. They're not SQL-like, they're not MySQL, they're not Oracle tables, they're not database files per se. Instead, FASTA sequence databases are text files. And text files represent a really, really common kind of input and output format for most bioinformatics tools. If you have data that you have received from a sequencer, you'll frequently receive it in FASTQ format. FASTQ is a big text file. If you deal with an XML dump of a mass spectrometry file, that XML is a big text file. Not that easy to read, but it is a text file. So in a lot of cases, when you're trying to interact with files in bioinformatics, you're interacting with text files. It's not universally true, but it's very commonplace. So the FASTA file on disk is this text file that has a whole bunch of sequence information within it. That is different from the name of that file on disk. So you will recall that in last week's session, we were dealing with a string that represented the name of the sequence database. But that name is not the same thing as the file itself. It's just the name of that file. We also, once we're dealing with these data programmatically, will typically have an object that represents that file. So the file object itself is, again, not the file, but from the point of view of the software it is. Because you can interact with that object, and in interacting with that object, you're also interacting with the file that it's attached to behind the scenes. And then the other thing that we need to keep clear is that, at least as we first go at this sequence database, we're going to be going through it on a line-by-line basis. So text files have this characteristic that they have so much text on this line, and then there's a return to the beginning of the next line, and then the next line of text, and then the next line of text, and so on. So it is possible to think of this file as a collection of lines, and going line by line is a very typical way to process these files. So those are 4 different concepts, and keeping them all distinct from each other is valuable. All right, so we start with the fact that text files contain printable characters and are separated into lines by EOLs. Have people seen EOLs? That stands for end of line. It's not a relative of LOL. I mean, we can laugh out loud at these too, but that's okay. But so text files don't contain all possible values inside them. Have you ever tried to open something you thought was a text file and you saw a whole bunch of weird looking characters that, yeah, so that's not what's going on with a text file. A text file is going to contain only printable characters and will be separated into lines by these end of line characters. On Windows computers and Linux computers, you're going to find a difference in how end of line gets encoded. But I'm not really going to go into that difference at the moment. Just keep in mind that the text file is going to be printable characters only and be separated into these lines. So when we open a text file, we have a lot of different modes available to us within Python. So we're going to focus only on reading information from the FASTA file. In this case, we're not writing a big text output as well, nor are we making any modifications to the sequences in the sequence database. That means that we're going to use kind of the most basic of modes for talking to that FASTA file. We're just going to use the R read-only type. If you were to open that same file with a W mode, a write mode, you would overwrite data that are present in that FASTA file. Now, it's frequently the case that you want to modify an existing file, but not by replacing its contents entirely, but just by appending onto the end of it. So we have the A append mode, which allows us to append new information to a file that already exists. And there are some special modes available as well, but I'm not really going to get into how those play out. So our FASTA file is a text file. We want to open it in read-only mode, and that's going to give us access to its contents. So in keeping our discussion of Python parallel to what you'd see in a lot of other languages, I wanted to kind of walk through some of the basic functions you would see. So if you are trying to create a file object so that you can get access to the contents of a file, you might call it file object here. In this case, you would use the open function that's built into Python, and you specify that the file name associated with it. So we've already talked just a moment ago about these things that are not the file itself. The file object is going to represent that file within Python. The file name is that string of characters that describes where we can find it. And I think everyone remembers from the last slide that R at the end specifies that we just want to read it. So this is a very common way to deal with inputs within a Python program. Frequently, we have kind of a complex loop that allows us to sniff through the file for some particular string. Like, let's say you were trying to find your name in a long email archive or something. You could sniff each line by line and ask, does it contain my name? Does it contain my name? That sort of thing. So for that, you would use the readline method that's built into objects of file type. So file object being an object representing that particular file can have the readline method applied on it, which will return a string, which we then dump into a variable called thisLine. So that represents a way that we can grab information one line at a time off of the file. Now, there's a last piece of this that we frequently kind of forget about as programmers, and we can be very sloppy about it, and sometimes this really gets us into trouble. So I'm just going to point out that, especially when you are writing a file, it's very, very important that you remember to close it. Because if you fail to close a file and the software quits without your having actually closed the file after having added information to it, a lot of the stuff that you intended to write to the file doesn't get finalized off to the disk before the file object is blown away. So especially when you are writing stuff to a file, you must remember to close it. And that's what the close function is all about. You'll see that some languages include an explicit command called flush. I always kind of like that function. So if you have a bunch of stuff that's been buffered to go into this file, issuing a flush will force it all onto disk and achieves a lot of what you can do with a close. There's frequently a limit in programming languages on how many files you can have open at the same time. We know that some of the workflows that we do in bioinformatics can spray out thousands of little files. Like in the old days, we might spray out a pile of DTAs to represent tandem mass, each representing a different tandem mass spectrum from a raw file. That's a big example where you'd have a lot of files. So if you were to read all of the DTAs in a folder and forget to close them once you were done reading them, you would have all these open file handles, and a lot of languages bog down and behave very badly under those circumstances. Okay, so the basic workflow then that we're going to use to extract information from the files that we're reading in this software is to treat them through this big for loop. Everyone remembers that a for loop lets you iterate through all the different items in a set. So in this case, we're explicitly treating a text file not as a file per se, but as a collection of lines. So the file object then is our source of lines. It's an object representing this file on disk. It's already cut at end-of-line characters into different lines, different rows. So this line is then going to loop through each line of that input file so that it's going to represent the first line, then it's going to represent the second line, then it's going to represent the third line. And when we hit the end of file, EOF, the for loop is going to discontinue. It's going to stop because there are no more lines to process. So rather than go through the loop one more time on an empty line, the loop terminates and continues on. So in this case, we have the trifecta, right? We have the case where we are going to open the file object, we're going to iterate through the file object, and then we're going to close the file object. That's a pretty straightforward set of operations. Okay, and I think that, yeah. So that's going to be represented in this diagram by this can we read next business. You see, we're going to open the file, and at that point the software is going to kind of proceed ahead blindly with this attempt to open a text file, even without checking whether that file exists. Then we will proceed through a loop where we read each line of the file. We're going to do some statistics with that, and then we're going to report that. So what does that look like in the source code that we've got today? All right, so I think all of the code above this, where the blinking cursor is stuff that was there before, with the difference that I changed it to version 0.3 to reflect that we're making progress. Okay, so down here, we have been given a file name by the user on the command line. That's what this FASTA string was. We're going to attempt to open that file in read-only mode. And you can see that I've done what we call initializing a variable. I've got an accession count. Does everyone know what an accession is in a sequence database? Essentially, the accession is a label that we use to name every protein. So we have two different kinds of lines within these sequence databases. Sorry, that's really garbled on my screen, but so we have lines that start with greater than characters. Those are accession lines. This CCP 42723 is an accession number, and then everything else that appears on this line is all description. Okay, that's all one line of code, or one line of the text file. The second line is a bunch of amino acid letters. So here we see that we have a protein sequence starting with methionine and running on out to a final final KR there. Sorry, I just botched it. Oh, goodness, I garbled my file. That's embarrassing. There we go. So we see that we have multiple lines that we're going to have to process through in this. So there's a difference between the number of lines in the FASTA file and the number of protein sequences that are in that file. You see why that's different? So if I count how many lines there are in the FASTA file, I'm counting the number of accessions plus the number of lines of sequence. And the lines of sequence shouldn't count on that. So instead, what I want is some code that will recognize when the first character of a line is a greater than symbol, because that's special. Inside the FASTA format, the greater than symbol represents the start of the next protein. So we want this to be counted as a new protein. It should ignore all of this business, and then it gets to this line and says, I've hit another protein, and I can tell that because the first character is a greater than symbol. Okay, so how do we handle that programmatically? All right. So we're going to start by creating a variable where we're going to store the total number of accessions found in the file. Now we have our big loop here that's going to execute once for every new line of text within the text file. And you can see that right away we're starting with a check. Now I believe that we spent a little time with why equals equals is different than equals by itself. I'm going to repeat that because I think that's valuable. So if I start Python, I can try something like this string equals whatever is on my mind. All right. So this string has been, the variable this string has now been created, and we have assigned the value of that string to it. If I simply type the name of that variable by itself, I get back that value. Now I may not want to treat this as a string, but rather as a list of characters. So one of the ways that I can do that is to use square brackets to address particular letters within it. So this string 0 is the W. Oops. This string 1 is the H. The string 2 is the A, etc. So we're able to access individual members out of a string. All right, now can I do something a little crazy, like change an individual letter to something else? Ooh, didn't like that at all. Okay, so strings don't allow you to do an overwrite in quite that way. But in this case, I might want to ask, does this string, is it the same as whatever is on my mind? That's true. Okay, so we see that up above, I used 1 equals because I was setting the value of this string. But down here, you can see I'm asking a question instead. Equals equals means, are these two the same thing? The opposite of that is bang equals. Bang equals means, is this string not equal to that? Well, that's false, because it is equal to that. Okay, so the equals assignment operator is not the same thing as equals equals, which is asking, are these the same value? All right, so when we return to the code, we can see that we're using a combination of two things that we just did there. First off, we're using square brackets around 0 to indicate that we want just the first letter of whatever this line is. Next, we're using equals equals because we're asking as a test, is that first character the same as the greater than symbol? Okay, so I would point out that if we had the greater than symbol without the double quotes around it, the software would think we were using the greater than operator, which we're not. It is, by the way, okay to say things like, is 5 greater than or equal to 3? Is 5 greater than or equal to 5? Is 5 greater than or equal to 6? Right? We can do stuff like that. But in this case, we want to ask, is that first character, does it look like this symbol? That's why we have the double quotes around it. Okay, so in the case that the first character of a line is the greater than symbol, then we say, we are on a new protein. This protein is different than whatever came before. So we need to change the value of accession count. We see up here it started at 0, right? That's not very informative. We know it's set to 0 here. So each time we encounter a new protein, we want to increase the accession counter. That's plus equals. So if I have this value set to 0, and I say this value plus equals 1, what is this value currently equal to? 1. We see it evaluates right there. So however many times this value is incremented in this way, it's eventually going to have some number that takes into account how many times it's been incremented. So our metrics so far are really basic. I know I promised the FASTA Sniffer is going to do interesting things with all these protein sequences, but for now, we just want to change the value of accession count by 1 every time it encounters a new protein. And of course, once you're done with all that operation, it's really important that you close the text file. So fastafile.close makes use of the method for the file objects that will close that. And of course, we want to report to the users how many different protein accessions we found in the file. And in this case, we're combining two things. Remember that accession count is a number. So we're combining the string, we found this many accessions inside, with a number. And for that, we need to force that number to become a string so that we can report it side by side. That's why we make use of the string function. That's going to convert the number into a series of characters that can be printed. Then we print all done, and that's it. I would point out that programmers are often not very friendly with their users, and it's often very helpful when you're done processing a task within software to tell users that you finished successfully. So in this case, I've just added a little line at the bottom that says, all done. Great, so does it work? So I would pop out of here. Oop, I need to, it's okay. I need to quit from Python, and I see that I'm not in the right directory yet. So I want to move to where I put my software. Goodness me. All right, so I want to go to the UWC Python directory. There we go. I have all my scripts and things in there. And because I have Python on my path, I can simply type Python 20190725, that's today, goal3py. Now remember, if you just run it like that, we haven't given the software enough to go on. Right? So it's going to run the software correctly, but the software says, you didn't give me all the information I need. So I need you to provide me the name of a FASTA database. I hit the up arrow to repeat the last command. This time I'm going to type myco, and then I'm going to hit tab, because there's only one file in this directory that starts with myc. So now if I say Python followed by the script, followed by the name of the sequence database, I hit enter, and we see that took absolutely just a tiny amount of time to run. But did it actually sniff that whole file? Did it actually go through the text file? We see that we found this many accessions inside, 4,018 sequences. And then we got the all done message. Is everyone getting a result like that? Not necessarily. The result will be different if you run the goal 2 code rather than the goal 3 code. Because last week we hadn't written the stuff that actually reads the file. So if I run last week's code, it'll tell me I haven't given it a FASTA file name. if I give it the FASTA sequence database, it says, yes, it's the one we'll use, but it doesn't actually do anything with it. So all of that code relates to the goal 3 code that we added today. All right, so is that number a reasonable output? I think it's very important for people to apply a bit of sniff testing to their code, because the fact that the software compiles doesn't mean it's without bugs. The software, just because it executes without an error, doesn't mean it's without bugs. So is this the number of proteins that we expect to be present in the Mycobacterium database? Well, how about E. coli? People use E. coli a lot, right? So how many proteins does E. coli require to live? Is it huge? Is it tiny? E. coli is a pretty compact genome, yeah. So the number of genes it has, the number of protein coding genes, is pretty small. It's on the order of 4,200, 4,400, something like that. So a Mycobacterium tuberculosis is similar in complexity. They're both microbes. They're both bacteria. It's a Mycobacterium in this case. Yeast gets by with about 6,200 proteins. Humans have 20,000 protein coding genes, and from them we get something like 70,000, 100,000 different protein sequences possible. But yes, in this case, the software is producing the correct answer. This is the number of lines starting with a greater than symbol in that database is equal to the number of proteins that Ensemble says this microbe encodes. Okay, so that in brief is how to read a text file. And next week, we're going to start looking into handling errors a lot better. Let me just give a very quick example of what would happen if I gave it the name of a file that doesn't exist here. So instead of .fa, I'm going to use the name .fasta. So this is an example of kind of bad behavior from software. If the software is told to read a file and it doesn't exist, it's polite to tell your users, hey, that file name you gave me doesn't exist. It doesn't match a file in this directory. Instead, because we didn't check, we just tried to open it blindly, we got this error, a traceback, where somewhere in this line, a file not found error was generated. But if you, before you ever learned programming, got an error message like that, what would you do with it? You'd probably go to your PI and say, it didn't work. Because it's often very difficult to understand the error messages that software puts out. So next week we'll talk a little bit about ways that we can be better citizens in how we interact with files and give good feedback to our users about how to interpret what they're seeing. Okay, and with that, we're all done with today's Python for Biologists. Thank you.